Yeah, go ahead. You can start
Yeah.
presenting.
Can everybody just quickly put in a yes in the messages for the recording? Just to be, you know, thanks. Yes, okay. Alright, seems like we have most of the people in. Two, three, five. We have 14 people in. Alright, we can begin. Okay, so first of all, are there any questions from the previous lectures that you guys have did not understand or have been bugging you for 2 days? No? Okay. Um, Let me see if I can. Okay, there we go. Right. Alright. My screen is visible to everyone, I hope. Is there anybody who can't see the screen which has vision to extended single view and YOLO on it? Okay, I'll take that as everybody has the screen visible. All right. So last time we talked about how do we work with geometrical vision and how it is used in a particular library and how we can leverage that library to first detect an object in front of us using April tags, and further how can we use that detection to further extrapolate that detection to the future and find positions that we can base our decisions on, right? So today, what we will discuss and cover is not related to what you will get in the lab for this particular uh, section of the lectures, but it is useful if you want to go ahead and use it in your projects. It's very useful and it is very interesting. We will not be diving very deep into some concepts, but most of the concepts will be pretty much straightforward and give you a very good flavor of what is going on. So, all right. So to begin with, we will be extending the single view geometry, which we talked about in the last lecture, and we'll be talking about a particular kind of detection framework known as YOLO. It's not you only live once; it's you only look once. So, um, all right. So we'll cover the following topics today. First of which is multi-view geometry, which is an extension of single view geometry. Then we'll do a bit of look at a bit of object detection, and finally we'll discuss the lab assignment for a bit and talk about a particular thing which is more of a programming paradigm that you'll have to use in the lab in order to get it efficiently working. Right. So the first thing that we'll talk about is the multi-view geometry. As the name suggests, so far when we talked about single view geometry, single view, we had one view. Now that we talk about multi-view geometry, as the name suggests, we will be talking about multiple views. So a very simple um, path to begin with would be two views, right? So if I'm looking at a building, this particular building, from two views, say from here and from here, and I'm looking at this one single point, there are certain special characteristics that arise when you look at the same particular point in the world from two different views. And this thing, let's represent this into a schematic such as this, right? So one of my cameras is here, one of my cameras is here. The image plane for this cameras is this one, the image plane for this camera is this one, and we are looking at one single point here, right? So can anyone quickly tell me if they have an idea of what these variables are, beginning with say pi? What's pi? Anybody? Somebody has any idea what's pi or any other variable that they have an idea of? What's going on here? A good guess would be nice.
Is P the distance of the center of the image from the point of view?
Okay. Then what's lambda I?
Uh, the depth.
Right. So lambda I is the depth. Similarly, ui is the depth. Pi is the point in the image plane. Okay. And in this coordinate frame of this camera, pi is this point. Okay. And in this coordinate frame for this camera, qi is the same point but in a different coordinate frame. Similarly, small qi is the point, the same point reflected on the image plane, right? Now t is the translation of one camera with respect to the other camera, and r is the rotation of one camera with respect to the other camera. So, if we go ahead and analyze this diagram, we'll see that we are doing nothing very different. We are still trying to find a mapping between two views, right? Between two frames. In this case, the two frames are this camera, which has the point pi, and the other camera, which has the point qi, right? Now, if I try to write the point qi as transformed from the coordinate frame of pi, I will get something like this. I will get p multiplied by mu, because by multiplying with mu we get the xyz coordinates because mu is the depth, and then I transform it by r, right? And then I translate it by t, and I should get the point q, which is in this frame. Does that make sense? Any questions about this? Right. So just like we did something in single view geometry, I'm doing something similar in multi-view geometry, but in this case, I'm transforming my point from one coordinate frame to the other coordinate frame instead of from the camera frame to the image plane or from the world frame to the camera frame. This time I'm transforming my point from one camera frame to another camera frame, right? So having this formulation and looking at the same point leads to a very nice special feature of multi-view geometry, sorry about that, which we call as the epipolar constraint. So it's 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 easy to understand like this. So if this is a plane, right? So if my camera is here and my camera is here and I'm looking at the same point where my fingers match, it is essential and intuitive to understand that all of these 3 points will lie on the same plane because it's a triangle, right? They cannot be warping unless the lines are curved. And since light travels in straight lines, we are pretty sure that this x, then this point, and then this point, all of these lie on the same plane. Now, them lying on the same plane helps us in a way of getting rid of the depth variables, which we do not know and have been troubled by since the past lecture. So, the lambda and the mu, because we know that this lies on the same line, we know that the volume of this shape will be 0. Hence, if I do a qt, if I do a triple cross product of of these three vectors, qt rp, which is the vector p in q's frame, and the vector t itself, I should get a 0 because this is a plane and hence it will not have any volume. So by doing this very small trick, I am able to completely get rid of the lambda and the mu. Does that make sense to anyone? Everybody? Are there any questions about that? Because this is a very important concept to go forward.
I have one question.
Yeah.
With what is the rotation R respect to?
Rotation r is the rotation of vector. So this r is transforming this point in this coordinate frame to this coordinate frame, right? So essentially, this equation is entirely in this q coordinate frame. So rp is essentially is in this coordinate frame. If it had been just p, it would be p is just in this frame, the p frame.
Okay. Sure.
This entire equation is in the q frame, right? Any other questions? And yeah, when we formulate and we write equations, it's I'm not going to say absolutely, but I think it's important that we write it in one single frame because well, uh, it's one single equation, so we write it in one frame so that all the variables are in a single frame. So this equation is a simple triple cross product of volume, which should be zero because all of these vectors and all the points lie on the same plane. Now, if you try to understand the epipolar constraint, it's very simple. Like I said, the epipolar lines. Okay, epipolar lines. So just like we have this plane, we also have the image plane. Now we need to understand. It's just a concept that the epipolar lines, which are essentially the lines lying on this epiplane, cross through the image plane. So the intersection of the epiplane and the image plane itself is the epipolar line for that particular point, right? And this is also what we this is also actually what we call as the constraint, right? Because now that we are talking about, you can look at it both ways. Now that we're talking about this plane, or do we talk about the epipoles lying on the same plane? It's one and the same thing. The epipoles lie on the same plane, the epipolar plane, or the entire all the three vectors lying on the same plane is the same thing. Questions, comments? Okay, there's a text somewhere. Okay, no texts. All right. Okay. So, like I said, by having this epipolar constraint, we have a wonderful um, trick up our sleeves that we can make the volume zero and make it this formulation which does not have mu and lambda, right? Does not have the depth. Now, the nice part about this is that having the epipolar line, I know that all the we see that this image having this point, right, no longer will have this depth ambiguity, right? Because we've gotten rid of the depth using our epipolar constraint. So having this formulation, what are we concerned with? We are concerned with the t and the r again, right? We are concerned with what is the transformation between these two views? How did the camera move, right? So if I have this t and r and I already know the q and p, which is actually just the image points, I can say that okay, combine t and r and I have a matrix E with this formulation, uh, qt q transpose e p should be equal to 0. I have something which is called the essential matrix, and the essential matrix is what we have to find out and further then derive the translation and rotation from. So there can be one more than one solutions to this essential matrix, right? And this is like something very interesting to know, and I would really like to see that if someone can like come up with one or two of these solutions, like not even mathematically, just intuitively think about if I have 2 points q and p and q, and I know that they are looking at the exact same point in the world. If I find the t and r using this formulation, will I have only one solution intuitively. Like if I'm looking at this X, only knowing the P and the Q, where all can this X lie? And how do I know that the R and T, which is actually what tells me where I am respect to each other, will there be more than one solutions and how many, or like what are they? Take a guess. It'll be nice. Anyone?
You only have 1 point.
Yeah, right now we're just looking at 1 point from two views.
I think infinitely many.
No. Well then, it won't work for us.
If it's only 1 point, it wouldn't work. But you have more than 1 point, no?
Yeah, right now I'm just taking the correspondence of 1 point. 1 point taken in two views. Still, there will be more than one solution to T and R. If I if I find this E and I know that this QT and P are in the left and right null space of E.
Can the point be behind the image plane?
Yeah, that's close. That's close. That's something that we are leading up to. Right? Something more similar to this.
I think there'll be four because, um, like, if you consider all the combinations of the points being in front or behind of both the frames.
Yeah, yeah, perfect, perfect. Yeah, that's what it actually is. So, looking at the camera and these being the image planes, I can have the point in front of the camera, both the cameras, behind both the cameras, or one of the image planes behind the camera and one of the image planes in front of the camera, and vice versa, right? So, the central matrix essentially will give us with more than one solution, which is four. Okay, so then it is up to us to have like a rational decision to take that where actually the image plane will be. But mathematically, by linear algebra, this will give us four solutions. Now that is a fundamental understanding of multiview geometry, and multiview geometry is used at multiple places. A common of which is if you have a monocular camera, you can move it around and over a period of time keep taking images and track features, and that is how a map is built, right? The 3D map, and you know the transformation of the camera as it is moving by finding the R and T. That's one way of doing localization when you can track features and transform yourself while you're moving. Another good example of multiview geometry is something we call as the stereo cameras. Um, is there anyone who is absolutely not at all familiar with stereo cameras? You can even message if you have trouble unmuting yourself. Is there anyone who has absolutely no clue of what the stereo camera is? First time they're seeing this word. All right, that's good. That's very good. So, the stereo camera is actually also a very simplified example of multiview geometry and helps us um, find information that a single view camera, which is a monocular camera, will not be able to provide us with. Okay, so now let's say that I have two cameras, right? And I have a fixed lateral displacement that I have provided it with. Okay, and now that I say that fine, I'm looking at this thing, which is a tree in front of a house, but I'm looking at it from two different views with a known lateral displacement. Can anyone tell me that where will be the epipolar lines in this configuration, in which plane? Anyone? Oh, Arnav. Okay. Arnav has never used a stereo camera. That's okay, you don't have to use a stereo camera. But are you not at all familiar with them also? Like, they exist. Yes, no. Anything? Or okay, that's good to know. If you have a basic idea, that's good enough. And the basic idea for anyone else who does not have an idea about is simple: two cameras put together at a certain lateral displacement, and they're looking at things from two different views. That's all the basic idea that you need. Instead of one camera, there are two different cameras, which gives us the multi-view geometry, right? So where will be the epipolar lines in this configuration and which plane? It's the same thing, nothing different. We have the epipolar lines in the same way for every point that we had in the multi-view geometry. It will be from the optical center, passing through the optical center of the camera and along the points that it's seeing. Fair enough. Now at this point, there has been a shift from what we were talking about in multi-view geometry before, which is this, to what we are trying to find now. Okay, so before what we said was that I have eliminated the lambda and the mu, and having eliminated that, I can now find the translation and the rotation. But in the case of a stereo camera, what I do know is that the cameras are in my hands, and I have the freedom to place it as I want. So the TNR that initially that we were talking about trying to find are actually known to us. Okay, they're actually known to us. So we do know the essential matrix, right? So what then? So now I know the essential matrix, and I have a point in this coordinate frame, and I have a point in this coordinate frame. What does that help? What does that help in? How can we be? 1 second. Okay. Does each point in the world give you an epipolar plane? Each point in the world will give you an epipolar line, which is corresponding to that point, and it would lie on the epipolar plane.
Right now, the triangle that we are seeing is the epipolar plane, right?
Yeah, yeah,
So if I have another point which is not on the plane, I'll have another plane,
yes,
another triangle.
yes.
Okay.
So think about it as the plane is not the triangle, but as a infinite plane, right? So if the point was here, right? So this would be like that.
Mm-hmm.
It's not a triangle; it's an entire plane.
Yeah.
Can I ask a question?
Sure.
Wouldn't that just mean that every horizontal line in real life would just be a plane? Not every point. So not every point in real world is going to be a new plane, but any horizontal line that is parallel to the camera plane would be a plane. Like all the lines, all the points that lie in that
Horizontal,
line
yes.
have the same plane.
Yeah, the horizontal lines, yes.
Okay. Thanks.
Right. So now we know that this is this, and I know the E and T and R. What do now will we be looking to find out? Which, if anyone has used stereo cameras, would know that that is the ultimate goal of the stereo cameras, why we do use it.
To find
Anyway,
that.
yeah, exactly, right. So in order to find that depth, so you answered that we need to find depth. Now let me just go back a bit and ask, what was the initial goal that we started off with? The initial goal that we started off with was to find the position of what we are seeing in the world, because in this case what we are finding is P and Q in the image plane. We do not at all have the information about where is this point actually in the camera frame, right? How far is it, and how far it is in terms of depth, which is Z, and in XY coordinates. We don't know about that. So knowing that was our initial goal, how can knowing this ETR and the points in the plane help us that? Points in the image plane help us in that. So that was our goal, to find the position of every point in the camera frame in the real world. That is our goal. So think about what information do we need to find out the position of a pixel in the world code or the camera coordinate frame. What is the information that you will require, that if you're given a pixel and you are told that this is a stereo camera, so you know E and T are, what information do you need to find the position of a pixel in the world? Any takers? It's a very fundamental question, applies not just to stereo cameras, like just anywhere. Just information based. What do you need? Anybody in messages?
The horizon,
Which horizon?
like the camera plane horizon. I mean the world horizon.
Um, uh, I think you're talking about the point where the vanishing lines meet, something like that.
Oh yeah. Yep.
Right. Yeah, that's one way that you could think about getting the information that you need. But
Can you repeat the question?
I'm sorry, what? Okay.
Repeat.
It's on the screen. Like, what information do you need to be able to figure out the position of a pixel in the world? That's correct. We need the focal length. We already know that by E and T. Yeah, that's intrinsic. Yeah, we know that. Correct. That's correct.
Camera intrinsics.
Yep, that's correct. What else?
Lambda and mu in the image.
Perfect.
Like that.
We also need to know the depth. It's similar to single view geometry. It's the same thing. It's exactly the same thing that we did in simple view geometry. We need the intrinsics. We need the depths, right? So what information was provided by able tags was the
Corresponding.
detection, right? We detect the able tags in the image plane. That's the first thing, that we need to know which pixels actually correspond. Exactly that. Soumya, I think, said that. Right. Whoso said that? Yeah, exactly. Which pixels does it correspond to what I am seeing, right? Corresponding features. And what information do we have? We have the camera intrinsic parameters, as said by a lot of people, right? So if this is what we need, let's first talk about the first thing that we need, the pixels. How do I find the pixels that I'm interested in finding the position of, right? Then the camera intrinsic parameters. That's also I know. I have the pixel coordinates. I have the camera intrinsic parameters. Now, depth of the pixel, we have multiple ways to find this, which we'll talk about. Right. So, how do I take advantage of a stereo camera, knowing that it provides us with depth, and how it provides us with depth is what we'll talk about in a second. How do I take advantage of the stereo camera to solve the problem of finding the position of a point in the world frame? So for that, we'll have to first talk about the stereo camera itself and how does it help in providing us with the depth, right? So just looking at this picture, what you can see if you look closely, such as here, this white portion, right, and this white portion. You can see that this white portion is big and this white portion is small because this is two views of the same corridor from two different cameras or from two lenses of the same stereo camera. What you will notice is that if I superimpose one image on top of the other like this, objects which are close seem to have shifted a lot, while the objects which are far have not shifted a lot, right? That is similar to like what you have seen. Um, if we knew everything about the Aper tags, do we still need two views? You don't need two views if you're doing an Aper tag geometry because Aper tag provides you with features by contour tracking. Does that answer your question? Cool. I mean, you can still use two views with April tags to do different things. Maybe make it more accurate, things like that. But if for the only purpose of finding the pose, April tags works pretty well. Yeah, you can also use P3P. That's something we will not cover in it, but if you want to look it up or talk to me later about it, we can have a talk about that. P3P is also an algorithm that you use when you have single view or multiple views and try to track points and find. Essentially, it is used a lot in 3D reconstructions. Right. So moving on, talking about stereo cameras, we have an intuitive understanding that if we have two views, just like our eyes have, things that are far away seem less shifted and things which are close seem more shifted. That's the very reason if you bring your finger very close to your head, you'll kind of see two fingers, but if it's far, it doesn't matter, right? So knowing this, how can this help us? So think about it like this. If we do some geometry in this view, that I am using a camera C and a camera C dash, and both of them are seeing the pixel which is in the Fourier world as X, and in the pixel frame it is at X and it is as X dash. If we do simple high school geometry and apply similarity of triangles, we will see that X minus X dash, which is, it's a little confusing, but X minus X dash is essentially this distance. Okay, this distance is X minus X dash, right? And we know that I have the baseline as this. Okay, no wait, oh sorry, I'm sorry about that. X minus X dash is this distance. Okay, X minus X dash is this distance. So X minus X dash, and if I bring my F down here, so this distance upon this distance is equal to this distance upon this distance. Just simple similarity of triangles. We know even if you make this triangle and this triangle, it will give you the same result, right? Simple geometry, pure geometry. But what this helps us is in finding the Z depth, right? So I know the pixels, so I can find X minus X dash. I know the baseline because I formed the stereo camera myself. I know the F, the focal length, because I know the lens that I've used. Hence, I can find out the depth, right? So now we have one problem solved. We know the depth. Now the next thing that we need is a ray which defines the point in the world frame. Now what do I mean about that? Suppose in this coordinate frame I know the Z, right? I know the Z. But what I don't know is the x and y, which is this x and outside of the, like protruding out of the frame of the screen, the y. What I can do is I can try and find this ray, right? And when I say ray, what I mean to say is maybe I can find out the angle theta which this ray is at, and I don't even need to know the distance or the length of this ray. It's a ray, so it has no distance. But if I can find theta and I know z, I can very easily find out the x, right? And I can find out the y. Does that make sense? Any questions? All right. So we need to find the ray. How do I find the ray? So now that we have seen a lot of intrinsic parameters and a lot of R's and T's, let's sum it all and see what this gives us. I have a camera frame. I have an image plane that I said was at a z distance. I had my pixels, which after dividing with the z gave me u and v, and I have my world in which I'm seeing a pixel, right? So if I'm seeing this point, right, if I'm seeing this one point and I make a ray from my camera center to this point, which is actually in the world, what I can see is that it passes through the image plane and the pixel frame in a way that I know where the v and u is, right? So again, if I look at it as only triangles with geometry, if I have information of this point in u and v or in x and y, can I not just simply find out the angle that this red ray makes with x and with y, right? So that is exactly what we can do. Since I know the intrinsic camera parameters or the projection matrix and I know the pixel coordinates, I can form this ray. I can form this ray. Okay, so if you remember, it's it's a little confusing here. It's used like changeably somewhere, but at some places I found them to be different, at some places I found them to be the same. But essentially, if I go way back, um, where was the homogeneous coordinate thing? Yeah, here, right. So here we said that the image plane was at a distance 1, right? But when we are calculating for a certain system and I get an x, y, and z, and then I divide that vector by z, I get an x and y in the pixel frame, right? So the z actually was not 1 for the image plane. It was based on how the camera was constructed. But if I bring it back to the pixel frame, I divide it by z, right? And that's when I get the pixels, by dividing it by z. And then let's just get back to the original slide. Yeah, so at a distance z, I found the points as x, y, z in the image plane. Now if I if I divide it by z, then I actually have x, y, 1, and those x and y are in the pixel coordinates, which are also then like shifted by the optical center and then divided by the scaling, all those things, the intrinsics, right? So I know the intrinsic camera parameters and I know the pixel coordinates, right? Now if I know that, I can project this pixel back somewhere in this point, which has the x and y, And if I have the x and y coordinates of this point in the image plane at a distance z, I know the angle of this ray, of this red ray, which I know for sure will extend and pass through the real world coordinate, right? So now what we needed was, from this diagram, is if I have depth, which we know we have now, and the angle, which we now know that we have now, I can find the position of this point with respect to either of these. Okay, so now I have said that I need the projection matrix, right? So let's talk a bit about what this projection matrix is. Similar to what we have seen in the in the single view geometry, you have the focal lengths fx, fy, you have the optical centers, and you have the trans. But the addition that there is this tx and ty, which is the translation of the stereo camera in the x and y direction from each other, the difference between them, right? And the simple thing that you have to do is that the ray x will be, the point x will be the pixels x minus cx minus dx, the optical center, and the translation. The ray y will be the pixel y minus optical center minus dy, both divided by the focal length. Simple pinhole camera lens model. I'll get the ray, the xyz, in the image plane, right? Now, again, we have the ray. Is there anything else do we need to define the point in the world frame? Anybody? Okay. The depth, which we have already talked about, and the stereo camera has helped us in. Okay, so essentially that's where we have the advantage of the stereo cameras. If we have the depth estimates and we have the intrinsic camera parameters, we can find 3D global coordinates of every pixel in the image, right? And this is something that you can use. We have depth cameras, recorded bags, if you want to use that as a project, and you can use that to find actual positions of the pixels that you're interested in, right? And there are like OpenCV resources, that you can use to facilitate that and not code the entire thing yourself. Okay, so
Can I ask a question here?
sure.
If we can get the 3D point cloud, why is it that we can't use this instead of a LiDAR? Is it because of the camera intrinsic parameters are not as good, so we have a really, I guess, large...
Noisy. Yeah.
Yeah, so like for large distances, we wouldn't be able to get an accurate point
Yeah.
cloud? Is
Yeah.
that the
It
reason?
doesn't. It doesn't.
Okay.
And it's noisy for, so like the, yeah, also field of view. LiDAR has a 270 or something field of view. The camera only sees what it sees. It's probably like 90, 120, 130, something like that. Even a wide angle. So yeah, so A, it's noisy. B, field of view. C, what is the distance that is accurate to?
So when you say when it's not field of view, when you say it's going to be noisy, why is it noisy? Is it because of the resolution, or is it because of the intrinsic camera parameters? Like, are there cameras?
Multiple reasons. So the intrinsics, we can to some extent say that are accurate to some levels, not absolutely, but say like pretty accurate. But where we do lose, yeah. So in the comments, as you can see, feature matching, how good are your correspondences, right? Unless you're not able to like correspond your pixels accurately, absolutely accurately. Processing, yeah, like the real sense does processing on board, so it saves up a lot of that. Um, then resolution, yes, but not the only factor.
Wait, do we need feature mapping for just getting point cloud?
Um,
I thought you know
so
where the
yeah,
cameras
yeah, yeah.
are with respect to each other. Do we need feature mapping? Because
No,
we're not
you
really
don't.
detecting anything
Yeah,
yet.
yeah, yeah. So when you're just calculating the depth of every single pixel, then no. Uh, but it's more like, how do I say this?
How do you get depth of each pixel? Like you need to know the corresponding pixels in images, right? For each image, for each pixel.
But don't
Yeah,
you know where
you
the cameras
do.
are? But you know where the cameras
You
are,
know the
right? So you
camera,
know
but
their
you
field
don't
of
know
view
when.
too. Well, you know field of view
Sorry.
of the camera, and you know the field of view of the camera and where the cameras are with respect to each other. And you want it for every single pixel. So do you need to know?
Yeah, you
I don't
need
know.
to
I
check
guess
every point on the corresponding epipolar line.
yeah, but do you need to match it? I guess I'm
Yeah.
confused why you need to match it to a different.
Like if I
So,
give you two images, how would you know which pixel corresponds to which one?
Well,
so
that would be
since
the case if you don't know where the cameras are. Like two random pictures, you want to like relate the two images. But in this case, you know where the cameras are with respect to each other.
yeah, that
So
is
I
the
don't know
thing.
why you need
So
mapping.
yeah, yeah. So let me point it out to you in this way. You do have two cameras, right? You do have two cameras. Now, the two cameras. Hmm, yeah, the x minus x dash. That's good. That's a good catch. Right. This payment, this x minus x dash, right? So
Hmm.
when you have two different images, so even if you like go here, right, and I say that the left camera is looking at the center pixel of this ball, and the right camera is looking at the center pixel of this ball.
Hmm.
So yes, that's calculated by correspondence. So um,
What? I
the
guess this is the
cameras
part that I'm
themselves
confused.
know, yeah, the camera themselves know where this pixel is,
Yeah.
but what the camera cannot tell the other camera is that, okay, fine, if you're looking at the center of this circle,
Uh huh.
right,
Uh huh.
of this ball,
Yeah.
give me that exact pixel, give me the intensity of that exact pixel, because in
Yeah.
this because in this view, this
Uh
could
huh.
be like 23,7, and in this view it could be like 17,6, right? So
Hmm.
how does this camera on the right tell the left camera, okay, this is my 17,6 pixel and this is your 23,7 pixels, and these are the same pixels that both of us are seeing for the same feature?
Yeah. So don't you have like both cameras have the fixed resolution and they have fixed
Yes,
number
they
of
do.
pixels and they have fixed
Yes.
like we know the intrinsic value of it, both
Yeah.
of the cameras
Yeah.
and we know where they
Yeah.
are in the world. So for each specific pixel, you are just finding the values of two cameras, the difference in the two camera values.
Yeah.
And
Absolutely.
for that specific pixel, you find the depth. So I don't understand. I understand when you don't know where the cameras are, you need to match the features. But I'm
So
confused why you
yeah.
need to feature map for finding the depth. I just want to know if I need feature map to find the depth, if I know where the cameras are.
You might be confusing as like with a feature map. Um, what we've talked about so far. It's not exactly a feature map of what you might have on your mind. It's more like so like what you did in scan matching, right? I have
Mhm.
two frames, right?
Yeah.
Um, and I need to find the R and T between the two frames. In this case, I do have the R and T,
Yeah.
right?
Yeah.
So when I do have the R and T, so
Hmm.
I know that when I transform this point to this point, right?
Hmm.
it will. I um.
I guess what I'm saying is that the
It's
point, the feature, is the pixel. The pixel itself is the feature. Like the
Yeah, the
two
pixel
cameras.
itself is a feature, right? The pixel itself is a feature. So
Yeah.
if we go back and this, right? This.
Yeah.
So how do I confirm that I know this TX, right? I know this E, which is in the middle, but
Mhm.
how do I confirm that the QX QY and the PX PY are actually looking at the same point?
How do I know if the both of them are looking at the same point?
Yeah. How do I know that this px and this qx qy and this px py, what it's seeing is not slightly shifted, right? I
Mhm.
made a decision to to have this px and this qx in my calculations,
Mhm.
but what did I base this decision on? That's the question.
Um, I don't know. I guess I see what you're
Yeah,
saying, but maybe I'll just leave it
yeah.
and then ask
So
later.
that's
But
like that's what you match. Yeah, we can talk about it later in office
yeah, because
hours.
I feel like I don't want to like slow everything out. We can talk about it
Yeah,
later.
that's okay. But like what? So it's the question initially was that what are the reasons why it has noise, right? So it's one of the reasons
Yeah.
that
Why do we use that
if
except lidar? Which yeah.
yeah. So multiple reasons: field of view, um, uh, accuracy of calculate of matching, then what else? What else? What else? What else? What else? Processing, how fast this is processing, and if we are losing information, then mirrors. Um, so I don't have that, but if you see in this picture also, white walls, white walls kind of vanish or become very noisy. That's because while matching, the intensity
Mhm.
is it's the white wall problem which you see in like mapping also. That if you keep seeing, if you keep moving and you keep seeing a white wall, you'll think that you're not moving, right? So
Mhm.
even in this picture, if you see here, like this person is pretty nicely visible, but here and here, all these white things, they're all kind of not showing up nicely,
Mhm.
right? So it's kind of like that. Okay, any other
Thanks.
questions? Any other questions? Mihir, was your question answered? Mihir? Yeah, you do need feature mapping to get the values of nx and x dash. Okay, I'm guessing that was answered. Now, so far so good. I have I have the I know that if I have knowledge. Okay, there's Google links here. All right. Okay. Okay. So Soumya has posted in a. Okay. Okay. I did not see there was so much conversation going on. Oh, shit went down. Okay. So yes, feature mapping is required. The slides posted are nice if you guys want to go through that. Um, yeah, I think that answers most of the questions. Okay, so any other questions? You can go through the slides that Soumya posted if you have time later. Right, so now we know that if I have the pixels, I can find the depth and I can find the ray of light and hence I can find the XYZ coordinates. Okay, So now we'll roll back and get ourselves to ask a bigger questions, which is how do we actually choose the pixels, right? I know that if I have the pixels of the object that I'm interested in, I can find its XYZ coordinates in the real world. But how do I find the pixel in the first place? So that's where detection comes into play. And that's why we will do YOLO. Okay. Alright, makes sense. I hope it makes sense to everybody. If not, ask. Cool. So now we need to know the pixels that we are interested in and that we have to detect and find the coordinates of. Alright. YOLO is one of the very good detection frameworks that have been used in the past few years, still being used in multiple places. I have used it a lot of times. It is very fast and it provides simultaneous classification of objects and regressions, and it's just pretty good. And there's a link to the original paper, the version 3 paper, which is the last one. I'm guessing it's the last one. You can go through it if you're interested. So we'll talk a bit about YOLO, not in depth, just a bit, just to give you a flavor. So the first question, why is YOLO actually fast? Um, First of all, it is a single flow architecture. For those of you who are not very familiar with convolution neural networks, it's not always the case that you input an image or input a data and then it goes through a number of convolutional layers and then it gives you an output. There are architectures in which input goes through a few convolution layers, then one single input, and the output of that goes through another set of convolution layers, and the same output goes through a different set of convolution layers, do something else, join together, go through another convolution set of convolution layers, and give you an output. Not in the case of YOLO. YOLO is a single flow architecture, and the advantage of this is that it performs regression and classification simultaneously. Now, what I mean by regression is classification is that regression is where the object is in the image, and classification is what the object actually is in the image, right? Can you guys give me one moment? I'll be back from the restroom and some water because I'm thirsty. Be back in a sec. Yep, got water. Um, the single flow and multiple flow architectures. We'll talk about it because we'll also talk about probably also talk about architecture which has more than a single flow, right? So regression and classification. Regression, where actually is the object in the image, and classification, what exactly the object is in the image. So I need to also find out the position, that is the pixel coordinates, and then I also need to find out what these pixels represent, right? So that's regression and classification. Now, no backbones or different branches, which is the same as a like it's a single flow. There are no backbones which give you a certain output, and then output goes through certain more convolution layers to give you the final output. Nothing like that. Also, it generalizes to only one task, that is regression classification. It cannot, most probably, it cannot be used, or it cannot be like cut into half, and the output can be used for something else or like that. It might not seem very clear right now, but in a few minutes it will be, hopefully. Right. Now, this is the example of an architecture which is not single flow, right? So it has multiple branches. Like faster CNN, it's it's not a good architecture. I don't like it. It's very hectic to code, but it has its own advantages, right? So it has a backbone, right? And the output of it goes through a different set of two different branches. Image goes through 1, 2, 3, 4, 5, 6, 7, 8, 9 convolution layers, gives a feature map, gives a feature map. The feature map goes through certain more convolution layers and feature vectors to a softmax, to a regressor, and give you object proposals. Now, this object proposal goes to this branch along with the original feature map. Together, they go through ROI pooling, more fully connected layers, to a softmax, to a regressor, and finally have the output of where the object is and what the object is. Is this clear now? That how does the difference between like single flow? Yes, 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 that is correct. If you take CIS 620, if you take CIS 620, which is Advanced Machine Perceptions next semester, you will code this. 680, yeah, CIS 680 next semester. You will code this. It will kill you, but you will code this. Yeah, it will kill you. Payment knows. You can ask payment. Uh, yeah, so yeah, it proposes the regions. This is the region proposal network. It proposes the regions, and it gives you a feature map. It gives you regions of interest. So essentially, propose a region, then the next network looks only in those regions, finds the regresses the bounding boxes, and then says, okay, fine, this is the bounding box that I'm looking at, and this is the classification. Now, the advantage of this is that I can use any of these separate branches and use them for doing something else, right? So instead of pulling that here, maybe I branch it off and use the region proposals or uh, or the object proposals for doing predictions, anything like that. So that's one advantage of having yeah, you can get back to me. That's one advantage of having this multiple branch architectures. Now, detection with YOLO, we'll go through it. How does it happen in a brief way, so that it's clear at an abstract level, more of an abstract level. Essentially, those of you who have not taken like vision in learning classes, it's okay. We're just going through an abstract, and most probably, if you choose to go ahead with the YOLO way, you'll get a trained network that you can use and perform all the multi-view geometry that we talked about. So, simply put, I take an image, I divide it into grids. Okay, I divide it into grids. Some people call it alpha boxes, right? Now, in this grid, I will start seeing regions having some things, right? So as you see in this, it started proposing, okay, fine, this seems to be something, this seems to be something, this seems to be something, but within that, it also is showing some bunch of garbage predictions, right? And all of them have some confidences. Then I see at look at the class probabilities. That is, okay, fine, I do have a garbage box here, but what is the probability of that garbage box as compared to other actual proposals? So I create kind of a heat map. Not in actuality, a heat map is not created, but I think of it as a heat map. I see, okay, fine. In this region, it seems like there is some class with a high probability. In this region, I think there's some class with a high probability, so on and so forth, right? Then finally, based on these class probabilities, I find out the final detections. There's a lot of hacks and tricks that go into post and post detections and pre-detections to make it work nicely, but it works very nicely, right? So for example, for each grid cell that we have here, I can have several possible bounding boxes that I want to look at, right? And these are called anchor boxes. So if I have this one blue cell, right, I can have a proposed bounding box, which I call an anchor box, like this shape, this shape, this shape, multiple. And that goes for every single anchor cell. Again, if you're not very familiar with this seem may seem a little cumbersome, but that's why we use GPUs. Streamline this. It's computation heavy, but it works, especially with GPUs. Right? So essentially what happens is that I have a proposed bounding box, which I call the anchor box, and then I regress that is make it large, make it short, right, to match the ground truth bounding box. Right? So what are the specific things that make it work is that we do define the grid size. The architect defines the grid size that we define depending upon how fine do I expect my image to be in terms of the size of the objects. Am I looking at big objects? Am I looking at small objects? I can define the grid size. To put some more perspective into this, small object detection is a domain of its own. So that will give you an idea of like, it's not so generalizable that if you want to detect a small stone, every grid size would work. Scale due to depth, you mean how big an object is or how small an object is? Yeah, exactly. That's what I'm saying, right? So if the object is far away, right, and if the object is so far away that it's so small that it is like a small speck or like not even covering the entire anchor box, then YOLO will have a hard time detecting it, and it does happen. And that's also where your how good the annotation was comes into play, right? So if you chose anchor boxes that were just big, yes, it has a prior. That's what the anchor box is. That's what the anchor box is. That a priori I say that I am assuming, and in the original YOLO, it's not just like one size. So it's like here I'm showing like 5, you can have like 50 anchor boxes. You can have 50 anchor boxes and you go through all of them and you regress all of them and check that maybe one of them um, regresses perfectly to fit the original ground truth bounding box which was annotated and predicts the absolutely correct class. So yes, there is an a priori for in this kind of architecture for what sizes might there be for each class. Does that answer the question? Cool. I mean, so this is something a little off the track, but this is something which I had also like realized once I was a little through with deep learning, which I'm not a lot through, but still, is that it's not exactly how we used to think about it. Is that you have a black box, you throw in a image, and something nice comes out. It doesn't work that way. You do have to give like a lot of a priorities. You have to do data preprocessings. You have to make assumptions of what the output should look like and will look like. And based on those assumptions and a prioris, is it able to work good? Otherwise, it won't be able to. Even like after YOLO, a bunch of post processing is done. You eliminate boxes which are overlapping. You eliminate boxes which are less, and a bunch of other stuff. So it does seem a little hunky dory right now. It's hacky, but apart from the black box that the neural network is, there are hacks that go into the entire architecture that make it work. The pipeline. Right. So discretize, find anchor boxes. We define the grid size itself. We regress the bounding boxes that a priori we assumed that the ground truth will have and can be regressed to. Simply put, like if I make this big of a bounding box, and in all my annotation, all my bounding boxes are this big, YOLO will have a hard time regressing them through that. So that's why we have multiple anchor boxes that we can regress to the original annotated bounding box, right? So we regress the bounding boxes by the anchor boxes, and we perform the classifications based on the confidence of what it's seen, right? And then we take the final detections by taking the top confidence scores and the best bounding box. Okay, what's regressing a bounding box? Fine. Suppose this image was actually your original annotated image, right? Or better yet, you see this box for the dog, right? But if I was annotating this image, which is more or less the case in today, with still like there are automatic annotations, but if I was annotating it, I would probably make it so that the tail is also inside the box, the annotated box, which I did manually, right? The ground truth. Now, if I made if I have the anchor boxes, right? The anchor box would be something like for each pixel, something like this, right? Say this one. Now I'm pretty sure that that anchor box will not perfectly align with this ground truth box. So regression is, can I make my anchor box height increase or width increase or both increase or decrease, like just manipulate the dimensions of the anchor box in order to get as close as possible to the ground truth bounding box. That's what regression is. Yes, exactly. Just adjusting to fit. That's all. Right. So yeah. So it finds the grid size. We define the grid size. We regress the bounding boxes by the anchor boxes, and then classification, and get the final result. The last version of YOLO, the latest version, is complicated. You take an image, pass it through convolution layers, right, and finds a fully connected layer. Then you take inverted layers and finally get an output here. So if you see, my image was say 448 by 448, and I took the grid size of 7 by 7. Okay. Ultimately, I have something of like 7 by 7 by 30. So let's talk a bit about what this output actually is interpreted by, right? So in each of those 7 by 7 30, with each 1 cross 1 cross 30, what is going on, right? The first 5 cells, the first 5 channels is what we call the cells in machine learning. In the first 5 channels, I have the say the bounding boxes proposed were 2, right? After regression even, I proposed 2 bounding boxes. Okay. So first 5 for the first bounding box, for the yellow one, for this anchor, for this grid, not the anchor, for this grid, I have the x coordinate, I have the y coordinate of the center inside the cell. So this bounding box will have a center somewhere here, right? So the pixel coordinate of that, the width, the height, and the confidence that there is an object in the bounding box. We're not yet classifying this fifth is not the classification of what it is. It's just the confidence of that there is an object there. Okay, it's called objectness, that there is an object there. Okay. Similarly, if I said that I will have more than one proposals, there will be another 5 channels there, telling it, okay, there might be another object here, and for this anchor cell, and it will have these properties: the x coordinate, the y coordinate, the width, the height, and the channel, and the bounding box confidence of objectness. Then I will have the classification probabilities, right? That for each of these classes, say we have 20 classes, what are the values of probabilities ranging from 0 to 1 decimals is the class. So we pick up the class with the best possibility. Now, can anyone tell me that this kind of output, what is the shortcoming of this kind of output in architecture? Because it seems like we are specifying a priori that they will have 2 bounding proposals, there will be 20 classes, and such things. Are there any shortcomings? Anybody? I kind of told the answer to you. Someone opened up their mic. Yeah, that's one reason why. That's true. It's not just scaling well, it's more like, how do I know that
You cannot have box an anchor for, like, if you have two or three overlapping objects, then you can just predict
Yeah.
2 of them.
Exactly. Right. So if it's an overcrowded scene, I'm more than sure that I'll be missing out on few detections, because I've a priori told the system that there will only be 2 most probable detections. Right. So that's one of the shortcomings of such kind of an architecture, where we specify that for each anchor cell, for each grid cell, there cannot be more than 2 or 3, or whatever we specify number of detections. Right, that's good. So now that we know YOLO, and I know that it can be used for finding the pixels of interest, how do we use it? Same thing that we were doing with APO tags. I can use YOLO to perform detections of things that are of interest and then gain information from them. So suppose that you have a stop sign, right? And you want to do something like include more behavior planning in your system. You can include YOLO to do those things. We can detect APO tags instead of using union algorithm that we talked about for detecting APO tags. We can just use YOLO to detect APO tags. We can detect drone signs. We can put in a sense of behavior, right? So, camera calibration. Okay, so now we will move on to the lab part, more of the lab part of this lecture section, and there is a camera calibration section in this. We will see that if it allows us with the logistics for you to be able to do camera calibration either physically or through a bag, If they allow, we will. Otherwise, it's just the knowledge that will count, right? So far we have talked about how to detect things that are of interest. Then knowing that we're detecting things, how do we use that information to find those things in the real world with respect to the camera? Any questions so far? Anyone? No. All right. Okay. So, camera calibration is something that you do very first before you start using a camera. Essentially, they're the intrinsic parameters of the camera that you need to calibrate, right? They're provided by the manufacturer to some extent, but even then, there might be some ambiguity. So, like, you fall your, you, you dropped your camera, it shook a little, the lens distorted a little or shifted a little. It would change the intrinsic parameters. So you need to calibrate that, right? So essentially, if we do that, if the logistics allow, we will use a checkerboard, right? Something like this. Is there anyone who has done camera calibration before properly, or everybody is unfamiliar to it? No. Okay. I'm assuming everybody's unfamiliar to it. All right. So you'll see that if the back file works, or if you can just print out a checkerboard and then use it to 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 perform the calibrations. But with ROS, it's pretty easy. You just have to use a package, and it does camera calibration for you. Um, what we do know, how it works, is that in the checkerboard we know the dimensions of the boxes, and what we try to do is that the camera has to understand that since it's a checkerboard and the parallel lines are parallel, it will try to make those lines parallel in the image also, and in doing so will make the intrinsics or the intrinsic parameters of the camera is correct, right? So when you use this camera calibration package, you will have to pan the 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 checkerboard left, right, up, down, so that in both the x, y direction and the size of the checkerboard are understood, and using that, it has enough information to calculate the intrinsics of the parameter, right? And so you see in this image, before it's calibrated, the lines which should be parallel are not really parallel. They are like skewed and curved, right? So once the camera does have enough information about the image, the calibrate button will light up. Just to press that, and it will write that information to your camera package, right? Now that it has been calibrated, see that the lines are parallel, right? The lines get parallel, so the camera now understands that this was the mapping by the camera intrinsics between what I'm seeing and what the image is. All right. So just a brief overview of what the camera intrinsics look like, just exactly what we have talked about in the single view geometry. For a monocular camera, you'll have something saved like this, where you have the K and the T. The K is the focal length. You have the width and the height. You have the rotation and the translation, which is nothing. Finally, you form the camera matrix, which has the focal lengths here and here, fx, fy, and you have the optical center, 306 point something. It's kind of the center of the image, but not quite, right? Kind of center of the image, but not quite. Camera centers. P is I think that would be one moment. I think P is used when you have a stereo camera. So you need the projection between 1 and 2, right? So that's why it's it's an identity matrix here. The P leads to here. It's just a vector, just like this R, just like this K convert into this. It is that, right? You have the distortion coefficients and you have the rectification matrix if it was a stereo camera. In stereo camera, you get the rectified image, which is the combination of the two images. It's identity because this is monocular, right? So then this leads us to the next question: is that what will change if this was a stereo camera, right? Any takers? What will change if this was a stereo camera? Yeah, that will change. Anything else that will change? Let's see. Camera intrinsic data. Yep, the projection matrix will change because then you'll have in this column you'll have the translation, the baseline, and you'll have some values in the rectification matrix also, right? But if you'll be using the able tags method, you'll be only using a monocular camera, and this will be more than enough to work with, right? Says other image information. If you have like, this is another way that the data is stored. So this was how it is stored in the INI file, right? This is how it is stored in the YAML file if you store it like that. This is an example of it's the same. You have the data, you have for the projection matrix, for the rectification matrix, for the distortion coefficient, for the camera matrix. It's the same, just two different ways of saving it. Right. Now we'll talk a little about the actual lab assignment. How do we use April tags to perform detections and then find the poses. We talked about this a bit before also, but we have the camera, the rectified camera image. We have the camera info, which is essentially this thing, the intrinsics. And what April tag provides us with is the tag detections, right? Which is this coming out of this. It will detect the April tag, and it will include the position and the orientation of the April tag and publish it as is. Right, so similar to what we have seen before, I have the April tag with ID 0 here, and I have the camera here, and I see the transform between the two. And if you see here, I have the X, Y, Z, and the yaw in degrees, which is how it is shifted with respect to the camera. This is not actually what it publishes. It publishes yaw, roll, and pitch too, but this is just what I'm printing right now because we are working in the 2D plane, so I was not going to run with this. Yeah. Then, right. So, what we'll be providing you in the lab will have certain things. So, we'll have a continuous detection.launch file. This is what you have to do. Like, we are walking you through this very nicely so that there's no trouble. There's a launch file. In this, you'll change the image topic and the camera info topic based on the camera that you're using or the back file that you have right here, and image topic and the camera info topic somewhere here, camera info right here. Okay, and that should start giving you the detections immediately. Right, that should start giving you the detections immediately. We're keeping this lab very light so that you have time to work on your projects A and B because you're quarantined. So, right, so you play the bag that we'll provide you with, or the camera that you might want to use. You run the continuous detection launch file, and it should start showing up and printing this information as is immediately. Now, what you have to do in the lab, the coding part that you have to do, is the post prediction part, right? So now you have to include the information that you're getting from the April tags library, and then you have to use that information to perform the predictions. So in order to do that, we'll use the same model that we talked about before, which includes both the linear model and the pure pursuit model. It's a weighted average, right? So what you should see is that if you subscribe to the poses of the April tags, and then you use the pure pursuit model to get the heading for the obstacle vehicle, and then you implement this prediction algorithm for say 10 seconds, and you're at a corner, it should show up that your car in the next 10 seconds will try to turn left as the pure pursuit path wants it to. Does that make sense? Any questions? No? Okay. Right, so yeah, so subscribe to the information from the April tags repository, implement the prediction algorithm, and everything else is in place to show up the markers. Or you might have to code it. It's your call. Right, so you can use this function, which is a part of the lab. It'll get the data from the April tags detection array and use that information. Also, it's an array because there can be more than one April tags in the view. So April tags library assumes that there can be more than one April tags in the view. So that's why it says an array. But one element of an array will correspond to one single detection and its pose and orientation. Post prediction. Right, and then you can use your pure pursuit algorithm, which you've already implemented, to find the pure pursuit path and the orientations that are calculated from pure pursuit, and use them in the same this part of the model. Right. So you would need the pure pursuit angles that we calculate through the pure pursuit algorithm. So those angles in the future callback, going there, finding the poses, particular poses in the future, and then you publish that as a visualization array. This is also, you have to perform the calculations and the predictions, and then you have to visualize the poses that you find. Also, if you want to find the velocity that the object is moving into, so that you can accurately find out where exactly it would be in the future, you can just take the difference between the two poses and assume that it's going to continue with the same velocity because the frequency is so high. Right. So essentially, on turns, the predicted marker should turn towards the pure pursuit path. On straight turns, it should be more or less straight, which is what we expect it to be. Nodelets. Okay, so up till this point, any questions? Questions, comments, anything? Okay, quick poll. The nodelets portion is a little, not a little, a little heavy, and it would be new to, I think, everybody. So it's 4 now. No, it's almost 5. So are you guys okay with more, which you have no idea about what the thing is, so it will be completely new to you? Or do you guys want to do this in the next class on Monday? Quick poll. Yes or no? Type it. Anyone? Next class is a yes. Okay, next class, next class, next class, next class. Okay. Next class. Okay. Okay, Somish can take a lot. Okay, next class. Okay, more people? No. Uh, Matt, are you around? Matt, has Matt left? Billy, are you around?
Yep.
Yeah. Next class we are going to do the project discussions, right?
Yeah.
Okay. Do you think it's okay if we do that in the next nodelets in the next class?
Do what?
Nodelets in the next class. It will take like 40 minutes, half an hour, 30 minutes.
Preferably not.
Preferably not.
Yeah.
Okay. Okay.
I
How about
don't know
this?
how long the project discussion is gonna go, so
Yeah.
let me
Okay.
ask Matt real quick.
Yeah. Because last time we did do nodelets like separately, so.
Hey, quick question.
Yeah.
Do we, at the beginning of the class, they were saying that the instructor told us that we're gonna say, or we're gonna like mention what topics we're interested in for the project.
Yeah.
How are we doing that? Are we like, is there a poll? Like, what is the process to get that?
Okay. Nodelets can be on Monday. Cool. Yeah, as opposed, yeah.
I was gonna Piazza post.
Yeah. I think I can just put up a if okay, so Billy, how about we just like can we just tell them the broad topics and then I can create a Piazza post of poll. A poll Piazza post.
A poll of what?
Like what are the things that people are most interested in?
I mean, we're gonna go over the options.
Okay, on Monday.
Yeah. Do you want to create it now?
I mean, they're asking if like they have to post anything right now on Piazza.
Because I don't know.
To tell-
I think the instructor told us something about having topics, like mention our topics that we're interested in at the end of the class. So I'm not sure what he meant.
Yeah. Do we want them to like tell us what they're interested in at the end of this class or on Monday itself?
The reports. I mean, it's not mandatory that you have to pick one right now. I don't know how the logistics are gonna work. The last year's project, not last year's project, I'm not sure how to share that. Would be maybe I'll find the slides from. Maybe I'll find the slides from all the presentations, but there's no like videos or anything. I don't think we recorded videos.
No, we didn't. I mean, the race was different from the project itself, so.
I can try to find all the reports.
Okay. Yeah, and I think like we'll do the project thing entirely on Monday. We'll have time to decide after that.
I mean, if you have some idea, I think somebody already did that. You could send a private post on Piazza so we know what to expect.
Yeah. Yeah, I mean, yeah, yeah, you can do that. Like after this class, you can just put in a private key as opposed to if you know or have an inkling of what you want to do. Right. Any other questions? Any other questions about RRT or Pure Pursuit? Since Pali is still here. Guess not. All right.
Oh yeah, one thing I think I added everyone to. I think I added everyone to the Slack channel that we have for the class, or at least most of you guys. If you, uh, yeah, I think most of you are in here, so it might be easier to post your questions there to
Yeah.
get like faster response. Yeah.
Cool. Okay. If there's nothing else, then we'll have to say bye, and we'll cover on Monday the remaining things.
All right. Thanks for
Okay.
thanks
Thanks,
for
guys.
everybody.
Bye.